Okay, thank you. Yeah, I'm going to talk about diffuse emissions in the galaxy. And I will start with the motivation and explain what I actually specifically mean by those diffuse emissions. So this is the spectrum of cosmic rays, which we've seen a couple of times last few days. And this is very interesting. It can be measured locally at the position of our solar system. And we see what kind of particles and which energy ranges reach us. But if you want to learn more about the transport of cosmic rays in the galaxy and how this would look like somewhere else, you need somehow non-local measurements. And one way to probe cosmic rays in other places of the galaxy is to look at diffuse emissions, galactic diffuse emissions. And this means we look at gamma rays or neutrinos that are produced by the interaction of galactic cosmic rays with galactic gas clouds or the interstellar radiation field. So if we now take into account cosmic rays like for the transport under their source distribution and cross-sections with the galactic gas or the interstellar radiation field, we can produce sky maps of the diffuse emission. And we have a good idea how those look like at the GeV energies for gamma rays. So this is a sky map that's been around since 2016 or 2012, the first results from Fermi-LAT. But we don't really know how those would look like at higher energies, so hundreds of TeV. And this is especially interesting because at those energies, we can measure the diffuse emissions of neutrinos. So the question I'm trying to answer is, how does the source distribution of cosmic rays has to be taken into account to understand the diffuse emissions at TeV energies? Because what one typically does is we don't really know where those sources are. As we've learned, those are supernova remnants, but we don't know the distribution in the galaxy of those. So one way to fix this is to look at the smooth source distribution. But one could also look at distribution of point sources. And the question is, how much would that influence the diffuse emissions? And would that maybe also break the relation between low and high energy sky maps? So what I'm doing is I model those cosmic ray sources in the galaxy at points, and my model of the galaxy looks like this. It's a cylinder, and we have a disk, the galactic disk, within which we are sitting, and also all the sources of cosmic rays are positioned in here. And then at a specific point in time and space, a cosmic ray spectrum is injected by a source, and then the cosmic rays diffuse in this volume. And I assume an isotropic diffusion coefficient, which depends on rigidity. So for those who do not know, rigidity is just the momentum divided by the charge, pretty much. So it's pretty much the energy. And then I implement some boundary conditions at plus and minus Z max. So the transport equation for those particles, I'm considering protons, looks like that. It's pretty much just the diffusion equation, because other energy losses can be neglected at the energies I'm looking at. So pretty much the protons would have diffused away from the galaxy already before other energy loss processes become important. Okay, on the right side of this equation, we have the source density, which depends on the coordinates in space and time, and a certain source spectrum, which is injected. Now, this equation is quite simple and can be solved analytically. And the solution of that for a point source, which is a Green's function, can be seen here. So we have this source spectrum, which depends on the energy, and we have pretty much a Gaussian and the correction factor to implement the boundary condition. So I have those two plots here to illustrate what that means. So for a plot of the flux independence of the distance in the xy plane, we pretty much see Gaussians. And those Gaussians depend only on the spread, and the spread is given by the diffusion coefficient and the age of the source. But if you look in the z direction, we have to implement the boundary condition. So this function theta here, this takes care of the fact that here, if we are getting close to the halo height, to this boundary, the Green's function drops to 0. Yeah, and I was talking about stochastic modeling. The reason for that is we don't know where the sources are, so we have to look at many different realizations of a certain source distribution and see what the outcome is. So I was considering this source density distribution. So we see here the density of sources in dependence on the galactic radius. And on the right side, you see the flux of cosmic rays, which is related to this cosmic density linearly on different points in the galactic disk. So it's just a top view on the galactic disk. And I'm showing here the mean of 100 realizations. And you can see it follows a little bit this shape of the density outwards, but there are also certainly some points that belong to individual sources that belong to some of these 100 realizations. And the expectation is if we draw more and more of those realizations and average them out, we should somehow get the same result as in the smooth case. And I've done that just as a check, and I have plotted here the flux of cosmic rays depending on the radius. So I have averaged over the angle in this plot here. And here you can see the relative difference between the expectations from a smooth source distribution and the ones from the mean of those 100 realizations. And those many different lines belong to the individual realizations. So you can see their mean agrees to the smooth one within 1%, but the outliers, especially to the higher fluxes that belong to just some very specific young sources, can get quite high. So if you look at some measures of the variance of those realizations, they can get quite high because the PDF of those has a very long tail towards the higher fluxes. Yeah, but I was talking about diffuse emissions, and this is one of the sky maps we can obtain from modeling such a source distribution and then plugging everything in, the cross sections, and the then integrating along the line of sight. So this is one of the sky maps, and we are able to calculate them very fast using basically matrix multiplication along those line of sights and some linear algebra packages, so NumPy. And yeah, now we are able to do that for many realizations and then look at the deviations that occur from the stochastic mean or also from the smooth source distribution function. What you see here is for one specific realization, the deviation in percent from the stochastic mean of 50 such realizations. And you can see that in certain points of the sky, actually this deviation gets as high as 13%. And very importantly, this is a diffuse sky map at 100 TeV, so already quite high energies. Now the question is, why do we get those deviations? And the answer is quite simple. Those belong to young sources that are within a few kiloparsec. I can also show you how those sources look like. So now you see, again, a zoomed in version of this top view on the galaxy. And here is the center of the galaxy in the sky view. And if you now follow from our position here of the sun along this arrow, you can see that, for example, this red blob here, this higher flux of gamma rays would correspond to the excess flux in this region here. And you can also draw this correspondence for the other regions and for each individual realization. So as we found out now, the diffuse emissions depend a lot on what the source distribution looks like locally. So we maybe should move away from an axial symmetric model, which might not be completely right. And we tried another model, which is the spiral model. which might be a bit closer to the future, but there are some caveats because we are not really certain about the spiral model in our galaxy. So yeah, we don't really know if that's really exactly true, but of course one can try and find out what the influence of this is. And now we want to quantify how high the deviations in different source models are. And what I've done here is to look at the standard deviation coming from 50 realizations in each model and normalize them to the mean of those realizations. And you see that in the axisymmetric model, so just the radial dependence on the source distribution, the fluctuations appear to be clearly lower than in the spiral model. But I must also say that in the spiral model, those deviations are driven up by few realizations with very high deviations. So to really make that clear, I have to do just more realization, more calculations. So now we have established that local sources really are important and have to be taken into consideration for diffuse emissions. But how about the connection between diffuse emissions at low and high energies for specific source distribution? And one simple guess would be that they are connected just proportional to each other, that the flux at high energies is just certain factor x times the flux at low energies. And if one translates that to the, so if one writes the flux of each of those pixels in the sky map as the mean plus the deviation from the mean, and then applies this factor to the high fluxes, then one sees that the deviation of the low maps should also be proportional to the deviation at the high maps. And just to show you that this is well justified, so for the stochastic mean at the low energies, which in this case is 10 GeV, to the diffuse emissions at 100 GeV is very well correlated. So this is pretty much just a straight line. What we've done now to quantify that for the other realizations is to plot the deviation at low energies against the ones at high energies. And what you see here is that there, all those points here are basically corresponding to each pixel of such a sky map, and the x coordinate is the deviation in the low sky map, and the y coordinate in the high energy sky map. And those don't really lie on one line. So a number to quantify this deviation from the proportionality is to calculate the correlation coefficient, which of these 50 realizations, and to look at their distribution. So what you see here is a histogram of those 50 realizations from the axisymmetric model and the spiral model. And one can clearly see that they are all away from 1, and only a few realizations are well correlated or moderately well correlated, and a lot are basically uncorrelated or only barely correlated. So this is an interesting point, because in this model there are some assumptions that we want to make better in the future. For example, it is very reasonable to assume that there are several different source populations that inject spectra at different energies, or that different energies are injected at different times from the sources. And all of those would basically mean that the correlation between low and high energy sky maps should go down even more. We are doing stochastic modeling, so we have to do much more realizations, and we want to make it possible by optimizing our computations, maybe by using GPUs, because everything of that is quite parallelizable. And yeah, by including other CR species and extending the CR transport model, we can also make all of that a bit better. Thank you.
Questions? I had a question. So here you already assume that the sources are in the plane. So there's no, it's not possible that nearby sources appear at high or low latitude I mean, so here basically the emission is triggered by clouds, I guess. So this maybe this is not so important if the source goes off the galactic plane.
I think one would expect that for close sources it could make a difference, but for sources a bit farther away, not so much. So at this point we haven't modeled it, but it's perfectly possible, even in an analytic model.
Yeah, so basically the radius metric model. Even then,
even then one can introduce a spread in the z direction and model the sources away from the disk.
Other questions? Okay. Does it seem to be the case? Then let's take Anton again and everyone in a second.